Okay, in your discussion, as we start this new chapter, we had some systems discussed. I hope, as you read and as you see now, that these are four systems also that you've dealt with in real life. And obviously, they're not going to be exactly the same style of systems when we work in the chapter, but they will be a series of things that are joined together to work for the same desired result or goal. So in a computer system, all the components work together. Same in the stereo system or audio system, school system, and then we have the digestive system. And of course, respiratory and all those others, but we have some human bodies, several different systems within our human skeleton, the skeletal system being another one also. So let's move forward and find out what our systems are going to be for Chapter 5. You will learn in this first section to be able to solve and graph linear inequalities in one variable, solve systems of inequalities on a number line graph. So we're going to deal with inequalities and maybe equations, but let's start out. They look like all inequalities. So look at these three different ones, and we will be solving each one separately. Solve each compound inequality. So that's the key right there. What is the difference between an inequality and a compound inequality? As you read, you hopefully picked up that a compound inequality has two or more pieces. So when you look at this top set in number 1, you're saying, hey, it has this equation over here on the left that I have to work out, and then there's one over here on the right, and it's separated by the word or. So that's one thing to be on the lookout for. In number 2, one inequality on the left, one inequality on the right, and we're separating it with an and. And last but not least, solve each compound inequality. There is no word in this one. There basically is an inside-outside look. Your variable's here in the middle, and it really represents this whole statement. And that middle statement gets used out here to the right, and it also gets used out here to the left. So we're going to be talking about 3 different situations here, but I want to be clear on what our and our or stood for, and still do stand for, from geometry. A quick real-life situation. If you have on jeans and a white shirt, you are a winner today. So you are a winner if you have on jeans and a white shirt. Okay, so notice I said jeans and a white shirt. How many people do we have in that situation? So look around. You might be a winner yourself. Now I'm going to change one word. What if I say you're a winner if you have on jeans or a white shirt? So same thing. Same combination of clothes. I'm not going to change that. You have on jeans and a white shirt, but I said that the first time, and now I'm saying jeans or a white shirt. What happened to our number of winners? And most of you will say, it went up. Oh, so from geometry, what did we say the and stood for? And I've got them sort of backwards here, so let's come down here. The and stood for the intersection, some people like to call it. The union. And you had that symbol, the intersection. Union's going to be the or. Intersection, and the symbol for an intersection was an upside down U. Intersection, what they share, okay, what they have in common, okay, common pieces. And that's all for and. So now go up to or. Or I said from geometry was the word union. A lot of people don't remember union. Think of it like the union of marriage. So two people join to become one, that style thing. So union. The union is a coming together, is taking all parts, all things that are included in both situations. So it's taking the part on the left and the part on the right and joining them. So union. all parts of both sets. Either or, some people like to say. And the union symbol in geometry was that upside or right side up U, it's without its tail. So we have intersection, we have union, and then down here we'll talk about this one when we get there. But think about how you read this. If I'm going to do this middle one, I want the answers that are less than 2, and I want the answers that are greater than -3. So I'm reading inside out because that's where the variable's at, and I naturally placed an and in there. So if it's an or statement, you're going to have to see that or in your problem, step 1. If it's an and, you could see it in there, but if you don't see it, that's the only time it can also be an and. So let's look at these three and let's actually graph them individually. So this first one, solve each compound inequality, state the solution set, and graph. So we're about ready to do that. If we were doing the or one first, they both look like simple one variable equations, so we want to get the x by itself. So keep in mind our goal is the x. And when we look at, there's the x on the right-hand side, there's the x on the left-hand side, your brain is saying, what do I have to do to get that by itself? I'm going to sort of solve both of them at once. You can do them one at a time. But on the left-hand side, I believe we're going to have to subtract 2. On the right-hand side, we're going to add 6. And remember, you're adding it to both sides of the inequality. When you do that, you can simplify, and you're looking at x is greater than 1 or x is less than -4. So there's our two solutions. And think again about being a winner. What does the or mean? It means union. I need everything in both sets. So we come down and say, if we're going to graph it, here's our number line. I need all the numbers greater than 1, which you can see over here on the right-hand portion of the graph, are chosen. And then all the numbers that are less than -4 are over here on the left-hand side of the graph. We have open circles because the signs are less than and greater than. They are not or equal to. So with that, we have our solution, all the numbers greater than 1, or possibly all the numbers less than -4. And that number line represents that solution. So you solved it, you stated the solution set, and graphed. So that was your first choice. It's an or. We graphed the union, everything in both sets. Second example is the one with the and in it. 1/3 x is greater than 2, and 1/4 x is greater than 2. Again, solve it. So I'm looking at find the x and get it by itself. So it looks like we're going to have to do some people would say a divide, but these are fractions. So let's use our rule, multiply by the reciprocal. So if we do that, I'm going to multiply by 3 on the left-hand part and by 4 on the right. And remember, both sides of that must change. So we're getting very quickly x is greater than 6 and x is greater than 8. Now remember also, we haven't done inequalities in a while. If we would have been multiplying by a negative, we would have had to switch the inequality signs to the other direction. We did not in this case because our numbers were positive. So continue on, we should be able to graph. Think about all the numbers greater than 6 and the numbers that are also greater than 8. And it's an and, so we want the intersection. So where do those two sets intersect? Does it look anything like this in your mind? Because it should. So it's an intersection that we graphed, and we did that because we had an and. Right? So the and stood for the intersection of those two sets. Again, it's an open circle because of the greater than inequality. All right, moving on. Next and third final inequality was that I like to call them triple. It has three parts, no words. Again, find where your x is located, and that's what you have to get by itself. So there's a little more work on this one, and right away I'm looking at, hey, that 5, it would make this problem a heck of a lot easier if we could just get rid of that fraction, the denominator, which is what's causing this to be a fraction. So we will take, instead of a divide by 5, we will multiply by 5. But remember how I said also that this is a triple? Well, that guy in the middle, 4 minus 3x, all divided by 5, has to be used twice. It has to be used once with the less than 2 and once with the greater than negative 3. So probably the first thing you want to do is write that series of 2 inequalities, or you can continue to work it as 1. Some of you like that because it's less confusing, but here's where I'm working it as 1. So I said first, go ahead and multiply by 5. Notice the fraction's gone. I have 4 minus 3x is all that remains, but now my numbers are 5 times bigger. All right, look in the middle there. If I was going to continue to solve this, I would have to get rid of that 4 next. The 4 is positive, so to undo the 4, I would subtract 4. But I would have to subtract it from, notice, 3 different parts. The middle is where I subtracted it from, the right side, and the left side. If you only do it to 1, then you're not really solving it totally. So when we subtract 4 and simplify, we now have this inequality remaining. Still has 3 parts. And now the only thing we have to get rid of is that negative 3 in front of the x, which is a multiplication. So let's undo that multiplication with division. And remember our rule for dividing by a negative in inequalities. You must switch the inequality sign. So we now have this statement. 19/3 is greater than x is greater than negative 2. Or really, if you read it inside out, which we prefer, x is greater than negative 2 and x is less than 19/3. Because it's a triple, and you heard me say and when I read it, you think of it as an intersection, and so now you are looking for where do those two sets intersect. X is greater than negative 2. Think of all those numbers. Then think of all the numbers that are less than 19/3. And 19/3, remember, is about 6 1/3. So I put an open circle at about 6 1/3 down here. And I put an open circle at negative 2 down here. Again, because they were greater than, less than signs, not greater than or equal to. And then the part they overlap in is the center portion. And on a triple. Now, solve the inequality. This one was not on that front slide, but it says and graph. This one has fractions in, and I would highly suggest anytime you see those fractions that you try to get rid of them. Makes your life easier. So when we got rid of fractions, our rule was multiply by the least common denominator. Our denominators currently are 3 and 2, so the smallest number they both go into, 6. And that's what you're going to see as our first multiplication. Every single thing in the problem gets multiplied by 6. So 6 times 1/3, 6 times 1/2, 6 times 4. The numbers that remain, if you cancel or just multiply, 2x, 3x, and 24. Inequality sign does not change. There's no reason to. But our x's are now on the same side. We can go ahead and subtract. We get a negative 1x. We cannot leave it as a negative x. We must simplify that. So to undo times by negative, we divide or multiply by a negative 1, which means, again, switch the inequality sign. And we did that times by negative 1 really on both sides. So we really were doing it here and here. So it did affect both sides, and because we multiplied by a negative 1, it affected that direction of the inequality. So we now have x is greater than or equal to a negative 24, and we're supposed to graph that solution. So check your graph. What do you believe it looks like? Here is what mine looks like. Find the number negative 24 down there on the left. It's a greater than or equal to this time, so it's a solid dot. Greater than or equal to, everything to the right is greater than, so you can see the blue arrow is my shaded portion of this number line. Next, solve this inequality and graph the solution. We're looking at, there's some distributing going on, there's x's on all parts of the inequality, both left and right. There are no fractions though, so let's just first get rid of those parentheses. 2 times x and 2 times negative 1. We've done that distributing now. Combine like terms over on the left is a choice. You could also even move the x's if you like. I chose to combine like terms first. Then I need to move variables one way, numbers the other. I chose to move the negative 5x, and that left us this. Negative 2 is less than or equal to negative 7. Now, think about that. Negative 2 is less than or equal to negative 7. Oh, negative 2 is actually to the right of negative 7 on a number line, which means it's actually greater. So that's why I say no. And so in this case, you have a false statement. And a false statement means empty set. And for those of you who like to say no solution, that would be another way to finish this problem. If you've never seen the circle with a line through it, other than like on traffic signs and things like that, it is your empty set or no solution. Empty set meaning there are no numbers in the solution set. Empty set symbol. Okay. With that, I think you've seen everything you're going to run into on section 5.1. A lot of review stuff, which is good, but that and or intersection union will be big. So work on that and bring any questions you have to class.